Hello everyone, and we're going to look at the second week of the Carbonate Lab. Now, Carbonate week 2. Quick recap. When we have sodium carbonate, it dissolves to make obviously sodium and carbonate ions. Okay, because carbonate is a base, you can titrate it with acid and see endpoints. Okay, now this can get a little confusing, but let's take it in two parts. As I mentioned in the last one, when you dissolve sodium carbonate in water, you have carbonate ion. Okay, and of course sodium, right, spectator ion. That solution will naturally be basic because obviously we've dissolved it, because carbonate plus H2O turns into hydrogen carbonate plus OH minus. Okay, so that's what we get. We get a little bit of OH minus, if you like, in the background. So if I used a pH probe, I would see pH approximately 10. Fair enough. So we're actually starting with a non-neutral solution. Okay, fair enough. Now that's kind of an aside because I don't want you to get confused with where the action is in this experiment. Okay, we're going to assume, even though the pH is actually up there at 10, we're going to assume essentially this doesn't happen for purposes of titration. Okay, and when we do our titration, and this is why we find the concentration of HCl of 3 significant figures in our first week, we're going to do a titration. So the carbonate ion, which is, if you think, the same number of moles of the original sodium carbonate. So it's like one of those shell games. Have you ever seen those guys with the little shells with the P underneath and you've got to try and find out where the P is? Keep your eyes on the carbonate ion, okay, because the moles of carbonate is what we want to find, and we can do that through titration. It gets turned into other things, and as we go we just keep track of how many things it makes, and then we can just, keep track of the number of carbonate ions. Now we're going to titrate with HCl, and if you look in the book there's a nice little picture of the drop counter set up to do this. Okay, so we can measure the volume of HCl added as a function of pH, right? Okay, and what we're going to do, I'll show you a picture in a second, we're going to generate a graph of pH versus volume or moles of HCl. Okay, all right, now that graph will of course start at a high pH because of the natural basicity of the carbonate. All right, anyway, the titration, this turns into HCO3 minus plus Cl minus. Okay, so when moles CO3 2 minus is equimolar with moles HCl, we see an endpoint. Now in a traditional titration this would be a color change. Okay, we're not using a colored titration, colored indicator here, we're actually just using a graph. Okay, so let me show you that graph real quick. So there we go, we start about a pH 10 point something, okay, and we add HCl, 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 and then we get a break. And when we get that point of inflection right there, this is what you'd see as a raw data set in your lab. That is volume HCl, and we can work out moles HCl. That is the moles of carbonate in there. Okay, so that's a very important number. Unfortunately, as you can see here, it's kind of a very subtle point. So what you can do, you actually take the first derivative. Okay, if you took the first derivative of that curve, you can much easily find out where it is. Now, if you look at our data set, because that is hard to see, they didn't actually write it down. If you took this with me, unfortunately, I'd have you do some other things, but we're going to take an easier route and just look at the second one, which is easier to see. But I just want to prove to you that, hey, there is a first, because carbonate is diprotic, or rather dibasic. Okay, we see that first point of inflection there, and that's when moles of carbonate equals moles of HCl, which equals moles of original Na2CO3. Okay, unfortunately, again, that data is not supplied to us, but we would sometimes use that. Okay, so fair enough, we just keep titrating. Okay, so if we keep titrating, and let's draw the graph kind of here. So pH, moles HCl, okay. We see endpoint number 1 where we see an inflection, and then importantly, because carbonate is dibasic, we actually see a second titration point. Where we turn this guy into this guy. Okay, so we see a second here. And that's what the data gives us, okay? So if we look at the data sheet, so, you know, you will have your own data sets, of course, okay? So if we look here, for this particular unknown, okay, and you'll use this information for your unknown, it'll be different numbers, but same procedure. Okay, that happened at 32.3. 32.3 milliliters, fair enough. Okay, so let's think about the math for that. Okay, let's think about the math of that. It's not a great graph, but that distance and that distance are the same. Okay, so twice the distance is twice the number of moles. So moles, original Na2CO3, okay, is that number divided by 2. All right, so if you work out moles of HCl at the second endpoint, divide it by 2, that'll be the moles of Na2CO3 originally. Okay, so let's kind of work through that. All right, so number 1, and I'll use this data set here. So I've got volume HCl at second endpoint equals my number, 32.3 milliliters, which equals 0.0323 liters. Therefore, moles HCl at endpoint equals CV, which equals, oh, bring it up, sorry. Always forget to do that. Okay. I need like a buzzer or something that goes off. So the concentration, now remember, this is from week 1. Whatever you got from week 1, that is the concentration you'll use for your HCl there. I'm going to just choose something easy, exactly 0.1, okay? So assuming week 1 I got exactly 0.1 moles per liter for my concentration of standardized HCl, times 0.0323 liters, that's nice easy math, 0.00323 moles. Okay, so I've got my moles of HCl, okay, at the endpoint, at endpoint 2, I should say. Therefore, let's move this up, which is a great thing about this is a paper, I can just do that. So, therefore, moles Na2CO3 equals moles HCl at end point 2 over 2, which equals 0.00323 over 2. Quick calculator. 0.00323 divided by 2 equals scientific notation, 3 sig figs, 1.62 times 10 to the minus 3 moles Na2CO3. Okay, fair enough. So we've got the moles of sodium carbonate in our unknown. All right, then, hey, if you've got moles of sodium carbonate, find grams Na2CO3. So, to find the grams of sodium carbonate, molecular weight, grams and moles. Moles equals grams over molecular weight, which equals, if I look at my data set here, here's my grams. You'll have a different number, but there you go. 0.398 grams over. I could work it out, but I have Google, so I'll just do it real quick. Molar mass, Na2CO3, 105.99, 105.99 grams per mole. So I work out my grams. Do the math quick. So 0.398. Oh, keep doing it again. The buzzer didn't go off. 0.328 grams. Sorry, 0.398 grams divided by 105.99 equals 3.76 times 10 to the minus 3. Nope, I've done it wrong here. All right. Sorry, this is a do-over. Okay, I got a bit distracted there. Let's do this again. So I'm going to start from moles of sodium carbonate. I need, and you probably were shouting at your computer, grams of sodium carbonate. Okay, grams of sodium carbonate. Molecular weight, grams and moles. Grams equals molecular weight times moles. Okay. In my defense, it's very early in the morning. All right, so we have molecular weight 105.99 grams per mole times 1.62 times 10 to the minus 3 moles equals, let's do that math. Makes more sense. 105.99 times 1.62 times 10 minus 1.62 times 10 to the minus 3 times 105.99 equals 0.172 grams. Now you're going to get a different gram number there, obviously, but work out how many grams of sodium carbonate were in that initial sample. Okay, now if we go back to the data set, you're going to use some specified amount of unknown. So to work out the percent weight from there, it's pretty straightforward, right? So percent mass Na2CO3 equals the mass of sodium hydrogen carbonate over the mass of the unknown sample times 100 for a percent equals, what we got, 0.172 divided by 0.398 equals times 100, 43.2%. Yeah, quite up to 3 sig figs, that's what our grade. Okay, there you go. So, all well and good, that's how you work it out. Now the write-up, obviously a little different than previous, okay? So if we check, let me just read through the write-up requirement, okay? There is a requirement for a lab report, okay? Do what it says, but no graphs. Okay, so basically you can have a table or two with the information I provided. Just copy and paste that over. Okay, if you want to see how to write up a formal lab report, how I like it, okay, you can follow the lab report instructions without penalty if you wish, which are in the packet. Okay, if you want to kind of do it in kind of a more kind of traditional way, there's the lab write link at the miscellaneous information. Okay, so I'm going to make this due in 2 weeks. It's the 7th today, so that's the 21st. Everyone, send me an email attachment of your lab write-up by April 21st is the intimidating red pen. Okay, so there it is. Hope that makes sense. Okay, so you're going to have some week 1 data tables showing me how you calculated the concentration of HCl eventually to 3 significant figures. Okay, and then the same workup we just did using that second inflection point, which remember is when you work out the moles of HCl, twice as many moles as the amount of Na2CO3 in the unknown, divided by 2. That's moles of carbonate, which is moles of sodium carbonate. Turn moles to grams, got your grams of sodium carbonate, and then just find out the percent of that grams in the grams of the unknown mixture you used. Okay. All right. If you do it right, good news is you'll all get a 100% on accuracy, because we worked out these unknowns to be perfect if you use the numbers correctly. So I expect good scores on this. I think traditionally people will, in the past have lost points simply because they didn't follow the write-up instructions. So just make sure you check all the boxes with regard to the write-up instructions, and I expect good things, right? Okay. So we are in this unusual situation where we're trying to do labs from home, so to speak. So I'm going to be pretty liberal with the grading on this. I'm going to give you every opportunity to get a good grade, even though you weren't in the lab. Okay, so follow these instructions, and I think everything will work great. Okay, I'll see you next time.